All right, welcome to part 2 of 3 for numerical solutions, right? Or numerical methods, right? Now we will talk about open methods. And the main advantage of the open method is that you don't need a bracket. But, if you want to, you can also kind of treat that like a double edged sword in the sense that if you only have one starting point, you are not sure if this open method will get you to a particular solution, right? And what better way to start off the open method with perhaps one of the most complicated, or not the complicated, but one of the most brain intensive methods, the fixed point iteration method. The thing about this now is that, well, it looks simple, but the thing is, it's going to be a little bit more difficult once you're actually going to have to try it yourself. Now, first, we are going to have to set our value to 0. Say, for example, right in here, we have x cubed minus 4x squared plus 10 is equal to 0. This is already set at equals 0. And now, what you're going to have to do, number 2, step 2, is perhaps the most difficult one in here. You're going to have to manipulate this equation, f of x is equal to 0, until you arrive at a new equation, which is g of x is equal to x, or x equals g of x. The thing is, there are no other instructions, right? Manipulate is such a, how do you say this? It's such a vague word in the sense that, well, what kind of manipulations are you supposed to do? What kind are you allowed to do? What kind are you not allowed to do? The thing is, there are no rules, right? So long as what you're doing, what you're manipulating is going to be correct, right? You should arrive at the answer. So something like this, right? If, for example, we have number 1, and here, x cubed minus 4x squared plus minus 10 is equal to 0. Let me just rewrite that in here, right? What you can do is something like this. Something as easy as, well, add x to both sides. Technically, you're already okay with this, right? This is already your g of x, if that is the case, right? You can do something like that because, well, technically you did nothing wrong. It's just that I have a pretty good suspicion, right? I have a pretty bad suspicion, but rather, right, that this thing will not lead you anywhere because, well, there is going to be a little what do you call this? There's going to be a little note near the end of the iteration method how to know when something is going to be good or not, right? As an iteration method. So we will have in here, let's just let me just write down the possible manipulations that we can do. One of them is that. The other one is, what I can do in here is get x squared from both of these parts, right? Something like this is equal to 0. What I can do is move, excuse me, move the 10 to the other side. You will have x squared times x plus 4 is equal to 10. And what I can do now is, number 1, separate the two x's in here and then divide both sides by this. What you will have now is x is equal to 10 over x times x 4. That's something that you can do. Okay? So, it's also, right, your g of x can also be equal to 10 all over x times x plus 4. Another one, what you can do in here is recognize that if you just move down the x plus 4, what you will have is x squared is equal to 10 all over x plus 4. And what you're going to do next may be the square root. This is also possible, although now you can see, wait a second, that may be a bit wrong because, well, there's also supposed to be a negative sign in there somewhere. But in this case, this is a technically valid way to go through these things. And now another thing that you can do is note that what you can move instead is this x squared. So instead of it being, right, x squared is equal to 10 over x plus 4, what you can do now is x plus 4 is equal to 10 over x squared. And then what you're going to do is minus 4. Put the 4 to the other side. So just from that, right, just from that equation, we've had what, 1, 2, 3, 4 manipulations. All of them are valid, right, as manipulations of the original f of x is equal to 0 equation. This is why fixed point iteration to me is one of the more complicated ones, because you don't know what the you don't know which ones are going to be successful. Well, technically you will know which ones are successful, but it's a bit hard to see at first glance, right? The thing that is so easy, right? The opposite to this, right? If getting to the manipulation is somewhat difficult, the easy thing here is that fixed point iteration is just that, getting fixed points. To get to the next iteration, what you're just going to have to do is your new x is just equal to you being able to substitute the old value of x in the g of x, in the manipulated function, right? And to test for convergence, what you're going to have to do is, excuse me, take the derivative of your manipulation in here, g prime, and then substitute it to your substitute your value of x. If in that case your x your result is less than 1, you can guarantee that it will converge. On the other hand, if it is bigger than 1, it will diverge, right? So you will not get anywhere. And as you can see in here, number 5 and number 6, replace the old value with a new value and then repeat until you get your value, or until your value of epsilon r, your approximate error, is reached. Okay, so let's try it with, I don't know, these 4 things right here, right? Let's have first x cubed minus 4x squared plus x minus 10, which I already feel is going to give us a bad time, because, right, to test for convergence, you're just going to have to derive. This is going to be 3x squared plus, what is this, 8x plus 1. And notice that all of these things are already positive, right? So that is not a great time, right? Even if you're going to substitute in here a negative value, right, this is still going to be positive, and well, you're still gonna have a bad time, right? And so probably not that. Let's shy away from that. Maybe let's look at the other manipulations here of your g of x, right? And let's just look at their what do you call this, their manipulations. G of x is equal to 10 divided by x times x plus 4, right? X plus 4. So you will have this thing, and then let's try and look at our g prime of x. Note that in this case, this g prime of x needs to be, right, needs to be, the absolute value of that needs to be less than 1. Let's try this now. There you go. And let's actually try this. G prime. Oh, there you go. So that means, right, using Desmos, of course, right, we can get here different values wherein your fixed point method, your fixed point iteration will actually work. So let's have here our original, which is x cubed plus 4x squared minus 10 is equal to 0. Let's have there our original x cubed minus, what is this? Plus 4x squared minus 10. You will have here only one, right? Only one, what do you call this? Only one root, which is at 1.36523, right? And what maybe we should put this in here. Maybe we should make this a little bit less. There you go. Maybe just make this one as well, just so it's not overbearing for everybody, right? What you can do in here now is look, there is this one root that we can go into, or rather that we can solve, and now we'll have to do is that we'll just test for this, see if it does work. Okay, now let's try this now. Let's just have, I don't know, a value, maybe x equals 1, right? Let's try out x equals 1. Number 1, if our g of x is going to be 10 over x times x plus 4, if we're going to have x equals 1, that's going to be, okay, never mind. That's going to be a little bit of a problem because it will not it will not converge, right? Notice that your x equals 1 is here. It is outside of the recommended range for your fixed point iteration, right? But it's going to have its, let's It's just going to diverge, right? So in this case, maybe we should try something bigger, maybe 2, right? Maybe 2. X equals 2, right? We'll give you g of 2 is 10 all over 2 times 2 plus 4. That is 6. Now this is 10 over 12. Note that when you're going to put in 10 over 12 now, 10 over 12, that is now going to be, right, outside of your fixed point iteration. So immediately we're going to say, okay, that will not do well, right? And so, okay, maybe we can try something like a negative 2 instead. Look at there, negative 2. Okay. What if now we try negative 2? Negative 2, then 10 all over. Negative 2 times negative 2 plus 4 is 2. So what we will have in here is negative 10 over 4, which is negative 2.5. Now negative 2.5 is, well, it's still inside in here. Still inside in here, negative 2.5. Oh, let me just send negative 2.5. Still inside, right? And now what will happen if it touches this thing? It will now be negative 2.667. 667. And now it is outside of that range. So apparently, well, this will not work. What if we have ridiculously negative values here? Like maybe, say for example, negative 6. What will happen? And at this point, right, you're already seeing, you guys are already seeing what is currently happening. We really are just trying to guess, right? We are trying to guess. Negative 6 times negative 6 plus 4, that's going to be negative 2. And look where we are. We were just in here earlier, 10 over 12. So, right? The conclusion is this thing sucks, right? This manipulation sucks. So what we will have to do now is, well, try and get something else. Most likely what will happen is that these polynomials will suck, right? These polynomials will suck, and so will these ones as well. Right? We need to find something that is a little bit more maybe precise. Maybe this square root will help us through. Square root of 10 over x plus 4. Try this now. Square root of 10 over x plus 4. Okay, this is showing good, this is showing good results, maybe, right? What is currently happening now is that you have this square root of 10 plus square root of 10 divided by x plus 4. The negative is this. Okay, that really doesn't matter. Okay, let's now try anywhere here. Maybe just 0 works. Maybe just 0 works. Let's try it now. Right? Try it now. Square root of 10 over x plus 4. We will have x equals 0. Let's try this out. We will have g of 0 is going to be square root of 10 over 0 plus 4. Now that will be square root of 2.5. Square root of 2.5. Let me reach for my calculator here. That's going to be 1.581138. 1.581139 pala. And then we put that in our g value, what is this? 1.581139. You will have 10 over this thing, this number, plus 4. Right? This number plus 4. There you go. And I can actually do this in my calculator. Plus 4. It will now give you 1.338562. 1.338562. And then if we keep going, my answer in here will go to 1.368635 or 636. And if I keep going, 1.364. Notice that it is already starting to get closer and closer to some number. 1.365285, 1.365223. Notice it's getting more and more accurate, right? And then 1.365230 or 231. We're getting closer. 1.3652299, so 230, and then 230 again, and then 230. That means, right? How many was that? How many iterations was that? That was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Took us 10 iterations to get to an answer where we are basically hovering, right, at, what is this, super mega exact values. Look at that, right? The epsilon r in here is basically lower than 0.000, because this is already what, 6 decimal places. This is smaller than this, 1 times 10 raised to negative 6, right? Which is very, very powerful. Note that in this case already, the epsilon value is what? Because the first 3 decimal places are already staying the same. Note, yeah, it's already way below 0.0001, or it's already near that value. So how many iterations was this? 1, 2, 3, 4, 5, 6. It took us 6 iterations to get there. So sometimes, right? Sometimes your fixed point iteration is good, right? Sometimes the manipulation is good. Sometimes it is not, and so it's whatever. It's whatever. So, right, what is currently happening in here? Well, what's going to happen in here is it's okay. I'm gonna have to remove this. What we're going to have to do is plot different values, right? Earlier we said that our starting position was x equals 0, right? And in this case, what I will do is that I will have 0 to g of x. Yeah. So now we can see with our eyes, we go up here, right? And that basically is our 1.58144. That's our first value, right? That's our first value. Y is g of 0. It's going to go from 0 to 2. What is this? G of 0. Yeah, there you go. What this is, right? What this red line is basically your x, right? This is a kind of a reflecting line if you want to think about it, right? This is your x, or maybe y equals x would be more accurate, right? This is basically just a kind of a reflecting line, because now our second iteration will be wherever this is, 1.58144. This is now going to be 1.58, or basically let's just say g of 0. There he goes, g of 0. And then we will go from g of 0 to g of 0 of 0. Oh, g of 0. You might say, what am I talking about now, right? We basically are trying to plug in this value as much as we can, right? Note that if you continue this kind of a staircase motion, right? This kind of a spiral motion, look at our values in here. G of 0, right? Gets closer, right? And what if we go g of 0, right? G of 0. Now it's getting closer to our fixed point. And now you're saying to yourself, okay, yes, it's getting closer to that intersection right there. What is that intersection? Well, this thin line is your g of x, and this diagonal is again your x. What this basically means is that their intersection is going to be x equals g of x, which earlier we just tried to we just manipulated. If your x is equal to your g of x, then that means that your f of x is equal to 0 as well. So if one value of x satisfies this orange equation, that means that it also satisfies the yellow equation. So basically, once you reach this intersection right here, you should be good, right? And so let's try this out in what do you call this? In another file, right? Another file. Let's have here. Let's put here our manipulation as well. Put here our f of x. Then is again SF Pro. Let's make it JetBrains. Okay. Your f of x here is going to be what again? X cubed plus 4x squared minus 10. X cubed plus 4x squared minus 10. You'll have that. And then now you will do what we will do pala. I keep doing ano. Just do this. Let's center everybody. Merge and center. My g of x in here, the thing I will put in here is what was that again? Square root of 10 all over x plus 4. Right? Let's have another g of x in here actually. I just want to see what that would do. G of x, let's try out the other one, which is, what was that? Where did we write this down? We tried, or we want to try 10 over x squared minus 4. 10 over x squared minus 4. Try this out. Okay. What we will do in here is we will have our iteration. And then our x, and then our g of x, and then our f of x. And let's just put in here our f of x. And maybe let's also put in here our error. Maybe. Let's insert here. Merge center this. Error. Epsilon r. Okay. Try this out now. Let's name these guys 1, 2, 3. Oops. Okay. Now, let's try here 0. And your g of x in here would be square root of 10 all over, is this c7 plus 4. Okay, it's your value. Then your f of x in here will be c7 cubed plus 4 times c7 squared. 10. Okay, it's negative 10. But we don't have our approximate yet. But what we will do now here is basically get this. And then we can drag this down. Oops. Drag this down. This. And your f of x, you can also drag down like this. And we will drag this down. Note that, oh my goodness, look at that. Your f of x turned, gosh, wow, look at that. It's the, okay, sorry. The scientific notation here suggests that the f of x gets very close to 0, right? It gets exponentially close to 0. Note, in here, it's already at 1.47 times 10 raised to negative 5. That's what the e means. And then in here, it's times 10 raised to negative 6, times 10 raised to negative 7, so on, so forth, right? And in here, your approximate value, let's just take this minus this c7 all over c8. Have this, and yeah, look at that. It only takes 6 iterations for it to, or maybe 7 iterations for it to go below or dip below our 0.0001, right? Which is amazing. Right? There you go. We can kind of pack that up there, and then everything in here is just us showing off, I suppose, right? Let's try in this case what will happen with 10 over x squared minus 4, right? Let's try and copy paste everything in here. And our g of x in here will now be 10 divided by x squared minus, whoops, minus 4. Of course, currently, yeah, it will divide by 0, so maybe that's not a great way to start us off, but let's have 1 instead, right? And then, yeah, you're gonna notice that it's already gonna go a little bit bonkers. Okay, so let's just have here, yeah, okay. And what you're going to see in here is that your f of x, oh my goodness. Yeah, look at that. It's going to parang bounce off. Yeah, it's just going to bounce, right? In here, right, what's currently happening is that it's not going to a particular value. It's not converging to a particular value, this g of x. And this also reflects itself in f of x, right? If we're going to keep doing this thing, yeah, it'll just bounce on and off and on and off. And well, it's not going to go to anywhere specific. right? So in this case, well, this is not a great iteration as well. So what we can see for a fixed point iteration is that it's not very easy to say whether something or whether manipulation will converge or diverge. But at the very least, we can turn this on your g of x and then have our little say as to when it should converge. Okay? So in this case, let's turn this g of x into 10 all over x squared minus 4. Right? So maybe a good first impression, not impression. A good first value would be something like x equals 4. Let's try in here x equals 4. Yeah, it's not converging. Look at that. It's not converging, right? There's even this very high jump in here. Suddenly it becomes 3,000 and then it dips down again. And well, we just can't see, or rather, it will not give us a good enough answer. Right? It will not give us a good enough answer. Okay? So there you go. That's sadly what is happening in here. In this case, it's 4. Okay, anyway. Okay. So that is our fixed point method, fixed point iteration. What if we have something like this, number 2? It's simple, right? I understand it's simple because it's a quadratic. The thing is, right? The thing is, with here, right, you can very well just quadratic formula, right? X squared minus x minus 1 is equal to 0. You will have an a equals 1, b equals -1, and then a c equals -1. And you can just put everything into your quadratic formula, negative b. So, you know what? Negative b plus minus squared b squared minus 4ac all over 2a. You will have in here positive 1 plus minus b squared is just 1. This is negative 4ac. AC is -1. So this will be plus 4 all over 2a, which is just 2. In this case, this will be 1 plus minus square root of 5 over 2, wherein in this case 1 plus square root of 5 over 2 is what you call your golden ratio. This is your phi, right? So maybe we want to get to that, but how will we do it, right? The thing about this again is that, well, you're going to try extracting quadratic. Like, okay, the thing about this is that, well, your x is already here, why not just put it there, right? So maybe let's try doing that, right? X squared minus x minus 1. We already know this is somewhat simple. So I will do as I'll rename this fixed point number 1. Let us copy this, move it to the end. We will have number 2. We will have x squared minus x minus 1. And then in here, what we will do, let's try a couple of manipulations. X squared minus x minus 1 is equal to 0. The first one that we will do is x is equal to x squared minus 1. Maybe that'll work, right? But let's have a little bit more. In here, we can extract, right, an x. Right, there you go. And you will now have x is equal to, you put this to the other side, 1 all over x minus 1. That's possible, right? And also, what you can do in here is x minus 1 is equal to 1 over x. So what you can do is just put the 1 to the other side. So you will have 1 plus 1 over x. Maybe that will work, right? And maybe what you can do pa is something like this. X squared is equal to x plus 1. So maybe let's try x is equal to square root of x plus 1. So we currently have 1, 2, 3, 4. Right? We have 4. So let's just try it out. Let's see what will happen. Let's try first our x squared minus 1. I know it looks stupid, right? Let's just try, right? In here we will have x squared minus x minus 1. Just apply that to everybody here. And then let's try g of x, which is just this squared. What is this? C7, right? C7 squared t7 squared minus 1. Then we will try this out. And look at this, right? You can already see something is very wrong because, well, it just oscillates, right? So this is also one of the very scary things, is that this may very well just not give you any good answers, right? So let's try moving this value of x. Maybe, right, we can see that maybe a 0.5 value might work. 5, and no, clearly not. No. Right? Okay. You know what? Let's try and consult. There you go. X squared minus 1. Right? Okay. So apparently it will only work below 0.5. Let's see. Let's see if a value will get us there. What about 0.4? Okay. It's not working. Look at that, right? Okay. What about a negative value, negative 0.1? Not working as well. Right? It appears that well, this is not the way forward, right? What about negative 0.4 maybe? Oh, wait a second. Oh yeah, I put everything in here na pala. I applied everything. Yeah. So it seems it's not working. Okay, it seems it's not working. Or 0.6. No, not working as well. Right? Apparently, there are two values to this thing, right? Yeah, there are two parang roots. There are two possible roots to this equation. One that is positive, right? This is your 1 plus square root of 5 over 2. And there's a negative one, which is the negative 0.618, right? Okay, so what are we going to do? Well, this is not very great. What about another one? Another one maybe 1 over x minus 1. Let's try 1 over x minus 1. 1 divided by x minus 1. My goodness, what is happening? There you go. Let's try this out. Let's drag this down. And there it is, right? We can finally see a value. And apparently the value in here is negative 0.618, right? So this is the negative portion. And let's try to see if we can find the positive value, right? Maybe a 1. Nope. Okay, never mind. This is supposed to be 1 over x minus 1 if I'm right. Yeah, x minus 1. So maybe a 2. Oh, it's just going to go. What about a 3? Okay, there you go. A 3 will get you to the negative still. Right, very interesting. What about a 0.5? To the negative still. Very interesting. Right? So apparently we cannot get to the positive root through this method. I mean, like you guys can have your own little suggestions in here, but apparently, right, the fixed point will always go towards, right, the negative value 0.618. Okay, as you can see, say for example, we pick a somewhat smart value in here. We pick a 0, right? If we pick 0, it will take us how many? Here, it will take us 13 iterations for us to get to our answer, which is very interesting. Very interesting. Right? Maybe a regular falsy, right? Kind of a what do you call this? A comparison with regular falsy may tell you, right, how effective the fixed point iteration is. But the thing about the fixed point iteration is that, well, so long as you get a manipulation, then you test it out, it's gonna be good, right? It's going to go to your answer no matter what your point is. Well, unless your point here is 1, right, or 2, or yeah, so on so forth, right? It will still get here, right? The negative 0.618, even if we play around with the value. Yeah, doesn't change it a lot. Okay, so yeah, you're going to see that. And what about 1 plus 1 over x? Let's try that. 1 plus 1 over x. 1 plus 1 divided by x. Okay, try this now. Maybe this will get us to our value. Oh, it does. This is for the other one. This is for the positive root. There you go. So if you have different iterations or if you have different manipulations, they may go to different kinds of values, right? And maybe the last one, maybe we want to toy around with is this square root of x plus 1. Maybe try this out. Square root of x plus 1. Let's have here square root of, this is I7, x plus 1. Okay, let's see if this is going to go anywhere. Oh, it will. There you go. It will. Let's delete this now and get us anywhere. There you go. What if we have our value in here, which is negative? Oh, it'll still go to the positive version. Very interesting. There you go. -6. Okay, sorry. Okay. Too much. Negative 0.99. Oh, it'll still go to there. I mean, like, so long as so long as it abides by the square root values, it will still go to your root, I suppose. Right? Okay, there you go. And yeah, that is it for the fixed point iteration. And before we go and discuss the superstar of the root finding algorithms, let's look at the secant method first, right? In calculus, in Caling 1, right? What we talk about is, in the beginning, what we talk about is the definition of a derivative, right? And basically, the definition of a derivative is the slope of a curve. You're saying, well, a curve has no slope, right? A line has a slope, but like a curve does not have a slope, but it kind of does at the tangent line, right? And you can say, and you can say to yourself, like, before anything, I mean, like, again, I can kind of get how there's a tangent line, but how do you construct it, right? Of course, what they're going to tell you is that you're going to have to apply the limit, right? With these 2 points, what you're going to do is that you're going to slide the point ever so close to your original point until they coincide. The resulting line before it all goes to 0 over 0 is going to be your tangent line, right? But in this case, we will have a cruder method. This is what we call the secant method, right? And what the secant method does is that it's also an open method, just like the fixed point iteration and just like Newton-Raphson method, right? The secant method, what it does is that it is a cruder version of the NRM, the Newton-Raphson method. What you're going to do is that you're going to substitute 2 initial values to f of x. It does not matter, or well, it may matter in the end, right? Which it is. And what you're going to do is that you're going to graph a line, right? You're going to graph a line between them, right? The secant line, right? In this case, the secant line may be something like this, right? And note that wherever it lands is here, right? That's going to be your x2. And now try and substitute that to the equation. So it's going to be somewhere in here. And now you're going to create a line between x1 and x2, right? And so now what you will create is something like, oops. What you're going to create is something like this. And now you'll notice that x3 is now somewhere in here. And your x3 is now this thing, right? And now you will create a secant line between x2 and x3. And now you will see, oh, wait a second, this is getting closer and closer to your answer. Now your x4 is here, and now notice you're already very near the answer. So that is the power of the secant method. Let's try that out, right? And well, if you want to know that the secant method is, it's basically just this, right? Get the new iteration by graphing the secant line, connecting x0 and x1, and then we will repeat so on and so forth, right? We will repeat. Let's try this out actually with this original one, which is x squared minus x minus 1. Let's try that out here. And then let's just get values of x equals 0, x sub 0, and then x sub 1. Let's have here 0 and 1. Okay. And then let's graph here x. How am I supposed to do this? X sub 0, x0, f x0. There you go. Then you will have x1, fx1. Okay, okay, never mind. They are going to create a horizontal line that's not going to intersect with anybody. Maybe let's try out 1 and 2. Maybe 1 and 2. There you go. We're going to have now is going to be a line between them. Right? Have a line between them. How are you going to do this? How are we going to do this in a smart fashion? Well, what I can just do, I suppose, is just get y minus f of x0. Then what I can do is get the m in here, m times the m in here stands for the slope between them, which is going to be f x1, f x0. Then in here is going to be x1 minus x0. There you go. That's the line between them. And notice that they will intersect at 1.5. What you're going to do is now your what do you call this? Your x2 will be 1.5. 1.5. And now we will add this here. Right? X2, f x2. And notice that now what you're going to have to create is a line between this and this, right? So the secant method is kind of a switching method, right? This old one will be replaced by the new one. This new one will be replaced by the newer one, right? So this is what we'll create, right? We will still do this, right? But now, or rather, let's just change everything, right? Instead of this being 1, this is now 2. This instead of 2 will now be 1.5. Now notice what you will create. In this case, the thing that you will create next is 1.6. 1.6. Actually, we can just get we can just kind of iterate on this by using this. Your new value is your old value minus this thing. Let's try this out. Your old value minus your f of old value times x1 minus x0. So your new value minus your old value all over your f of new value minus f of old value. There you go. So that is 1.6. Now notice it's there, right? And so we will now change 1.5 to 2 to 1.5, 1.5 to 1.6. You'll now see, oh, it's getting much nearer to our answer, right? So now notice, right, that we are creating a line between 1.5 and 1.6. And now it seems that our answer in here is going to be 1.619048. So now this is 1.6, 1.619048. And then there you go. We have to zoom in way farther. Now at this point, like, what else are we going to do? Your actual root, just so we know what the actual root is, 1 plus square root of 5 or 2. It's already way close, right? We get much closer. 619048, 618026, 618026. Yeah. So oh my goodness, we're zooming in already way too close. Look at that. 5 times 10 raised to negative 8. Right? We are already so close. Right? So that is now the power of the secant method. Right? So how are we going to automate this in Excel? Well, let's just have our x0, x1 as like an old and a new, and then a newer value. Have here your secant method. Let's make this a little bit bigger. Then your f of x going to, okay, again we have this jet x squared minus x minus 1. And then what we will have in here is your iteration, your x, and then your f of x, then maybe your epsilon, right? So you'll have here 0, 1, 2. We said earlier that our iteration was between 1 and 1.5. And 1.5, so this will be this squared minus this minus 1. And then this squared minus this 1. And we will drag this down. I will drag this down. We'll drag this down as well. Okay. And what we will do now for this new value is old minus, right? Old minus, we'll have a giant here. We'll have a giant fraction in here. What was that? Old times value of old. Old times value of old, which is this times new minus old, right? New minus old all over, right? Value of new minus value of old. There you go. Oops. I don't think this is. There you go. That is now your new value. And we will just drag this down. See if this works. And it does work. There you go. And it stopped itself in here because at this point they said, you know what, this is close enough. Let's see our let's see our epsilon of r in here. This will be, actually you can't even put this in yet. There you go. We'll start in here because these two first guesses were just by chance. Let's just have this value minus this value all over this value. Let's just drag this down. And it's already broken by iteration 8, right? So notice that the epsilon values are already way below 0.0001, right? At iteration 5, which is amazing, right? Let's say, for example, let's muck this up a little. 0. Didn't change, right? It's now at iteration 6, but in this case, wow. Okay, what about 0 and 1? That is okay, never mind. That is where it broke. That is because these guys were going to create a horizontal line. That is not great. So maybe that is one of the weaknesses of what do you call this? Of the secant method, is that if you're going to create a horizontal line, that's not going to go anywhere. Okay. What if we want to get to the negative root? Right. Well, what if we want to go to the negative root? Let's have 0.5, 0 and 0.5. That will go to the negative root. And there you go. It only took it, what, 9 iterations. And at this point, it got to 9 iterations because, right, it oscillated a little bit in here. Notice that it became -2, then became 0, then negative 0.03, and negative 0.75, and then so on. And, well, it got to its way near the end. The inherent beauty, or rather the inherent simplicity of the secant method, is the fact that you don't have to do anything, right? You just have to plug in 2 values and then boom, your answer will come, I don't know, sometime, right? Sometime in the future. And because of its relation to the Newton-Raphson method, right, what it's going to create is a somewhat fast, right, a really fast kind of convergence. This case, look at this, right? The epsilon value for what do you call this, for iteration 11 is already at 10 raised to negative 14 because it is so accurate already, or it's already so precise, right? There you go. That is the secant method. Let's go with another example right here. Oh, we have 2 examples, pala, rather. 2x cubed plus 5x squared minus 4 is equal to 0. 2x cubed minus 5x squared pala, plus 5x squared minus 4 equal to 0. And I think that's supposed to be plus. And let's just try this out. And here, 2 times this cubed plus 5 times 5 squared minus 4. Okay, and let's drag this down. Let's see how long it'll take us to get to our Okay, there you go. Okay, I didn't even have to change my iteration one in here, 0.5, but apparently there you go. Our answer is going to be 0.780776. Let's try and see if maybe there are different roots in here, but maybe let's give ourselves a little bit of visualization first. 2x cubed plus 5x plus 5x squared. Oops. Squared minus 4. Are there other roots? There are other roots. This is the first one we found. Maybe we'll try and find negative 1.28. So 0 and then maybe negative 1. There it is. There it is. Negative 1.28078. Right? So as you can see, how long did it take us? 6 iterations. Right? What about negative 2 in here? I feel like this is going to be a little bit more difficult. Oh, it's already at negative. Oh, sorry. It's already at negative 2. I mean, it got there. Got there. Then it said, you know what? We're already here. What about negative 3? And yeah, there it is. Oh, wait. No, this is not negative 2. This is negative 1.28. What about negative 4? No, it's not going to change it. Negative 3? There it is. Yep. There you go. It took us, what, 9 iterations? And in this case, like, no one in their right mind maybe would guess negative 4, negative 3. But in this case, right, the secant method, right? So long as you're somewhat a bit creative about how you're going to create your first 2 guesses, you can get there. Right? You can get there. There you go. That's our secant method. And of course, at this point, you guys know what's going to come next. It'll be quite a short video then, right? Part 3 of 3 will be the Newton-Raphson method, the superstar of the root finding methods. I'll see you guys there. Thank you very much.